Welcome to Telos and Physics. As you can see today, we're in the back of the room with an experimental setup. And what we're going to explore is a series of experiments where these two cars interact with each other. And so we're going to look and see how they interact in more of a qualitative way instead of quantitative. Although, as you can see, I have on the screen, I have the ability to measure speed. And so I need to turn that on, which I forgot to do. And so what we're going to do is we're going to measure the speed of these two cars as they go through these devices called photogates. So photogate is a thing you should know what it is. And what it is this has a beam of light that goes through it. And notice I have these flags, which are post-it notes, on top of my cars. Well, I know the distance that the width of the post-it note is, and so when it passes through the light beam, it has the ability to calculate the speed because it knows how long it took, and I told it when I programmed it that this is 7.7 centimeters. All right, and so when they pass through, so you can see that's the blue car, the red car is the top number. And so what we're going to do is there is a plunger on here. So we're going to look at explosions, basically pushing off each other. And so I push the button and that comes up. And so what I'm going to do is I'm going to set these next to each other. They're both the same mass. They're both about 250 grams. And so I'm going to tap this button, and I tap it with something else because if I push it with my finger usually sticks a little bit to that. So it's like an experimental thing that you realize after doing it a couple times. But when I tap it, I have a better job of not holding on to the blue car accidentally. All right, so let's tap it. All right, oh my, what good results. So notice the mass, well, the mass was the same, but notice my results. The speed of each car was identical. So let's think a little bit about this. So let's think about Newton's laws first. So Newton's laws, right? F net equals ma. It's a pretty handy one to think about. And so F net equals ma, but we're also going to need to think about Newton's third law especially as well. So essentially, well, why do I need to think about Newton's third law? Well, because the blue car pushes on the red car, but the red car pushes on the blue car with the exact same force. So I could actually say the net force of the blue car is the same as the net force of the red car. And so the mass times acceleration of the blue car is going to equal the mass times the acceleration of the red car. Okay, well, let's think about that from a Newton's law standpoint. So if the masses are the same, that means the accelerations need to be the same. Okay, but I measured velocity, not acceleration. Well, we can modify this, right? So let's go ahead and modify it, right? Mass equals change in velocity divided by change in time, and that'll be for the blue car. And then mass equals change in velocity divided by change in time for the red car. Okay, well, so my masses are the same. What about time? Well, the time that the blue car pushes on the red car, it's got to be the same as the time that the red car pushes on the blue car. You can't have one push the other for a longer amount of time. They're pushing each other. So when I have my masses the same, well, then the velocities must be the same. And that's exactly what we saw. Exactly what we saw. All right. So this term here, mass times change in velocity, actually has a name. And this is the way Newton looked at that. I'm going to write it up here, actually. So the way Newton really looked at this, so we had mass times velocity divided by time. Well, another name for mass times velocity is momentum. So momentum is mass times velocity, and I'm talking about change in velocity here because we're applying a force, and it's going from not moving to moving. So now let's see what happens when one is more massive than the other. So let's make the blue car. So this is a 250 gram mass. The car is 250 grams. So this is double the mass of the red car. So think about what we have here and how that's going to affect the velocity. Right? Think about that. So blue mass higher, red mass lower. What does that do to velocity? Think about it. Okay, let's find out. All right, that's why I have it set up. Let's find out. So 3, 2, 1, and tap. All right, look at that. So the top numbers for the red car, and the red car went faster than the blue car. Matter of fact, that red car went almost twice as fast as the blue car. Well, does that make sense? Well, let's look at what I have here. So really, the time is constant. So let's pull that out. So I got the mass times change in velocity of the blue car equals the mass times change in velocity of the red car. So this is change in momentum. Let me just write that just to be clear. Change in momentum of the blue car equals change in momentum of the red car. But we're talking about mass and velocity, so we really need this. So I said the blue car has double the mass compared to the red car. So the only way this could be equal is we got to double the velocity of the red car. All right. Well, let's see. So the blue car is the one that's pushing off, right? So let's put the mass on the red car instead. All right, mass is on the red car. Predict what's going to happen. All right, got your prediction? Let's find out. Ready, set, and boom. All right, just as we should have predicted. We now have double the mass on the red car, and so the blue car goes twice as fast. So the blue car goes twice as fast. Okay, let's add a third mass. Where's my third mass? Let's add a third mass to this and see if this keeps going. It should. It's physics, right? So we have triple the mass on the red car compared to the blue car. I think you know which one's going to go faster. By how much? All right, let's find out. Ready, set, and stop it before it goes through again. All right, so 0.35 times 3 is 1.05. Wow, that's pretty good. So you can see that just looking at different mass units with the car, we can use this idea. Really, it starts from Newton's second law, but ends up becoming something called the conservation of momentum, which we'll talk about in a lot more detail. But based on how the mass changes, then the velocity needs to change too. All right, we'll be doing some more quantitative problems in the future, but I wanted to show you how it works experimentally. So let's think about what we just saw in our demonstration. So answer this question. What happens when two carts push off of each other? Think about it when they're both the same mass and what are the comparable velocities going to be? Or think about when one has a higher mass than the other. How will the velocities compare? You can hit pause, think about it, and then unpause when you're ready to see the results. All right, so when they have the same mass, because of Newton's third law and Newton's second law, what's going to happen is they have the same mass, they have the same force, that's Newton's third law, therefore their accelerations have to be the same. Another way to think about this is it's also related to this new idea, conservation of momentum, where mass times velocity is going to be equal to the mass times velocity before and afterwards. And so we can see that here. Now, what about the cart with a higher mass? Well, that higher mass is going to have a lower acceleration. Therefore, it's going to have a lower speed because the force is still the same between the two cars. And so we can use Newton's second law, Newton's third law, and the conservation of momentum, which is actually related to Newton's laws.